Welcome to Buckeye Turf Podcast. My name is Carl Danneberger, Professor of Turfgrass Science at The Ohio State University. This enhanced podcast is the first in a series discussing the impact of temperature on turfgrass health. As an introduction, this podcast looks at the absorption and dissipation of heat from the turf canopy. Radiant energy from the sun is the source of warmth to our planet. It is this warmth that is the driving force for all biological activity. Life itself exists within a narrow temperature range, with most plant metabolic activity occurring between 50 and 104 degrees Fahrenheit. Little activity, except in some extreme situations, occurs below freezing or above 122 degrees Fahrenheit. Turfgrass plant adaptation is largely based on temperature. Cool season turfgrasses are adapted to cool temperate climates, represented here by the green regions, where soil temperatures are moderate to cool, while warm season turfgrasses are adapted to yellow and red regions of the warmer subtropic or tropical regions. Specifically, the optimum temperature for cool season turfgrass shoot growth is 59 to 75 degrees Fahrenheit, and for root growth, the optimum soil temperatures range from 50 to 64 degrees Fahrenheit. The optimum shoot growth temperatures for warm season turfgrasses range from 80 to 95 degrees Fahrenheit, while for root growth the soil temperature ranges from 75 to 84 degrees Fahrenheit. The radiant energy originating from the sun arrives at a constant energy level known as a solar constant. As radiant energy enters the atmosphere, energy is lost through various atmospheric processes. What reaches the Earth's surface, or the turfgrass leaf, is roughly 900 watts per meter squared, or 66% of the solar constant. Over half the energy that strikes the leaf is not usable. The radiant energy that hits the leaf blade is either absorbed, where only a small fraction, 2 to 3%, is used in photosynthesis. The remainder contributes to the heat load of the plant. Radiant energy that is not absorbed is either transmitted through the leaf or reflected. It is the net radiation, or the absorption minus transmission and reflection, that gives rise to the leaf and/or plant temperature. The two major means by which the plant can reduce its heat load is through the process of conduction, convection, and transpiration. This diagram of a cross-section of the leaf will be used to explain these two processes. Conduction and convection transfer energy from particle to particle, referred to as conduction, or by currents known as convection. The processes work together to dissipate heat from the leaf blade. The overall effect is that energy is dissipated from the leaf blade through the process of warm air rises and is replaced by cooler air. Transpiration is the evaporation of water from the leaf surface. This cooling process is a result of water changing from a liquid to a gas, resulting in a dissipation of energy. Transpiration primarily occurs through the leaf stomata. Stomata open to allow for the passage of carbon dioxide and oxygen during photosynthesis. While stomata are open, transpiration can occur. If the stomata are closed, transpiration stops. Additional resistance to plant cooling occurs when the boundary layer, which is a thin film of water or layer of 100% humidity on the leaf surface, that slows the cooling effect from conduction and convection. Heat and water vapor transfer in the atmosphere occurs through turbulent exchange, and a thick boundary layer restricts this exchange. The presence of wind or breeze reduces the thickness and impact of the boundary layer on heat transfer. Using what we know about radiant energy, conduction, convection, and transpiration, we can predict canopy temperatures. In this instance, we have a sunny, calm day. The air temperature is 90 degrees Fahrenheit, no wind, and adequate soil moisture is present for transpiration. Under these conditions, the canopy temperature would be 105 degrees Fahrenheit. Radiant energy, on average, increases a canopy temperature 15 degrees above the air temperature. Under the same conditions, except now clouds are present, the canopy temperature is the same as the air temperature. Under sunny, breezy conditions, the air temperature is 90 degrees Fahrenheit. The canopy temperature is comparable to the air temperature. In this case, the breeze increases transpiration and heat transfer, resulting in the cooling process. In this last scenario, we introduce a soil moisture deficit that will greatly reduce the transpiration power of the turf. In this case, a high canopy temperature can occur. Often heat stress occurs in conjunction with moisture stress. Radiant energy and the lack of transpiration explain why artificial turf can have a high surface temperature. The absorption of radiant energy and the inability to disperse it causes the surface to warm. The lack of transpirational cooling often results in artificial surfaces needing to be watered prior to practice to cool the surface, but the impact only lasts for 30 minutes or so. To measure more precisely, there are inexpensive, easy-to-use devices that can measure canopy temperature. This concludes an Introduction to Temperature podcast.